I'm actually not going to talk about my work, but I can't resist actually showing you some because I think it sort of bears some relevance. So I'm a sculptor. I teach in creative technologies and work across physical and digital media. And gosh, let's turn that a lot smaller than I had anticipated. Maybe I'm just going to, sorry. I can manipulate the form with my hands, which enter into a capture space. Again, there's some sort of sense of estrangement that goes on here from my body, which is really what I'm interested in, is the way that our normal spatial operations don't directly transfer into the modelling of the form in the same way that it might do if you were using a piece of clay. That, again, relational sort of structures form the coordinates rather than normal spatial coordinates. And then on the far side here, there's one of a series of works that I did, which are silver-plated 3D forms, printed forms generated from video that accrues over time. So you can see the video image above that, which is an image that is accrued and pixel values averaged, and then that's used to displace an image map, basically. So I'm not going to talk about any of that, but it does sort of feed into really what I'm going to talk about, which is materiality, spatiality. And so I'll start. It was early 2003 when I hauled my then state-of-the-art Power Mac G4 into my studio. And prior to this, it took pride of place on the white laminate desk in my office, where its clean contours and sterile surfaces asserted an air of technological superiority and, I hope, the contemporary currency of my practice. My studio back then was a sculptor's space, dominated by power tools, littered with a wide range of raw materials and half-made forms. There was scarcely enough room for this new digital material that I was introducing. This paper stems from an inquiry into the relationship between digital and physical media that started that day. It's an attempt to understand what happens as computers are given place on the workbench to unpack the methodological constraints and affordances presented by such a hybrid practice in regard to computer-aided design processes. In particular, I want to explore the impact of CAD technologies on student projects in the Faculty of Design and Creative Technologies at AUT, as a means of calling for a closer examination of the methodological consequences of such technologies in art and design practice. With around 35,000 desktop printers sold in 2012, and those are under $5,000 printers sold in 2012, and cheap 3D printers now as accessible as basic hand tools were. Not only is this technology accelerating to mainstream adoption, but it also is set to impact on artistic practice in the same way that video cameras, as a tool of conceptual art, further dematerialized the art object in the 1960s. While the uptake of video cameras was enabled by the introduction of consumer-targeted equipment, the current proliferation of 3D technologies has its roots in the DIY community and open source movement that thrives on the collaborative, decentralized studio of the web. This rise of the amateur that democratizes technology, enables creativity, and promotes self-reliance has both staunch open source components like Blender and processing and entrepreneurial streams such as MakerBot that have established viable and attractive business models. I'm going to talk over some of this without direct reference. The financial accessibility of 3D printing technology has put it in the hands of artists and is also supported by an increased ease of use and availability of open source software. And despite the popularity of 3D modeling software such as Blender, which I happen to personally loathe, the public is still not well versed in creating and using 3D models. As Basileri points out, education remains a significant challenge. as the ubiquitous print command suggests, generating a 3D form is now no harder than printing a page of text. What Basilio is identifying then is the gap between the affordances of the technology and the proficiency of the artist to realise those intentions. One solution to the education challenge has been to dumb down the CAD software to the equivalent of iMovie so that everyone can become the 3D equivalent of a cinematographer. An example here is Sculptio, which is one of many online printing services which have wonderfully banal enablings that you can send in a photo using your iPhone app and generate a vase which they will print for you on a 3D printer and mail to you for merely $300. So this sort of, you know, and likewise the interface that they have to you know, controlling or modelling 3D is really just a result of a series of sliders where you're operating sort of variable parameters rather than anything significant. As one of the dominant CAD software companies, Autodesk iPad apps 123D Design and 123D Sculpt embody many of the core conventions and methodological concepts of professional CAD packages. I'm going to return to those apps later as a way of illustrating concepts while avoiding the technical intricacies of professional CAD software. These simplified, user-friendly apps illustrate three interrelated issues that I want to focus on: spatial environments, material knowledge, and construction methods. Whether presented as a gridded plane or a gradated void, CAD software relies on the acceptance of an XYZ Cartesian spatial environment within which a virtual form is made. Cartesian coordinates are so central to the contemporary conception of pictorial and virtual space that it is difficult to visualize form without it. In the context of this paper, I do not intend to present notions of virtual space theory or alternative curvilinear form systems. However, it is important to address the implications of CAD-based Cartesian coordinates as a system that spatially positions and mathematically defines a space. Cartesian coordinates define an external universal logic that is in opposition to traditional subtractive and additive methods, where a material's mass and working properties are taken as a frame of reference. The abstract XYZ Cartesian framework sits like an immovable object, a movable grid over objects, the indices providing a point of origin that is a non-place that defines everything around it. Some quotes here that I'm not going to read all through, but you can no doubt read while I'm talking, so that's fine. In contrast with physical materials, spatial logic is frequently established by its own materiality. Parts exist relative to their constituency without reference to an external element. The material itself establishes the terms of reference within which the artist must operate. There is no externally driven parameter defining the logic of the work. This is most clearly evident, and there's a couple of examples here, in subtractive studio methods and minimalist doctrine of truth to materials, both of which identify material properties as spatial coordinates. In minimalism, truth to materials is simply an extension of the now romanticized notion of the sculptor's ability to visualize form within a block. Both accept the givens of a material as a spatial logic and reject external spatial structure. And this is a work by Smithson from the 60s, where he pours asphalt down a cliff. This is not to say that the body is not central in materiality. As Maurice van Kooten also points out, this knowledge is part of the process of creating sculpture. The tacit knowledge that Van Kooten is referring to is integral to sculptural practices that adopt a model of shared agency between the body and material within the work. In contrast, CAD models are commonly seen as being without materiality, without material properties. At best, these are applied as textures or simulated physics properties. this state of being without material quality other than that supplied by Cartesian coordinates and mimetic strategies is one of the key features that seems to distinguish CAD environments from the workshop. We may introduce CAD software to the workshop environment, but it will always somehow remain spatially differentiated from it. While the spatial environment is an obstacle to integration, it also affords a greater understanding of physical material processes that are also designed around Cartesian logic. A clear example here is something like this miter saw that is adjustable on 3 axes. Standard workshop equipment such as miter saws and table saws are not simply tools that dimension materials, but methods of subjecting raw materials to the Cartesian spatial logic that dominates the workshop environment. Set these plain. Oops, it's going to turn on there for me. It's okay. Computer-aided manufacturing systems, such as CNC milling machines shown here, can be seen as a logical extension of this method. Such computer-driven equipment translates directly from CAD files to material by following toolpaths determined by the CAM software. There's interesting content there about the structural method of slicing form up as a way of reproducing it, which is what happens in a lot of 3D printing, and how those toolpaths conceive and construct a form. I'm not going to go into, but probably well worth exploring. However, unlike the miter saw which students are taught to operate, CAM software is seen as requiring advanced expertise and is generally operated by a technician. Students and staff simply email a file, pick up the finished product in a system that mirrors Sculptio's print-on-demand service. Thus, despite the increasing ubiquity of this technology, the student researcher's conception of form is never confronted with material processes that realize it. Reconciling the spatial framework of CAD programs with materials and equipment is central to integrating CNC and rapid prototyping technologies into a workshop environment. Again, as graduate student researching in this area succinctly put, SolidWorks doesn't smell. The acknowledgement of the importance of tacit knowledge in practice should not, however, be taken as a statement that it is absent in CAD. It may instead be a matter of tuning our senses to the CAD environment so that we can begin to smell it better. As underlying structural concepts, construction methods play a central role in process. The same is true of 2 core approaches to CAD modelling: solid modelling and surface modelling. Each material has procedural logic and follows different workflows, which I'm just going to talk through a little bit. This is one of the reasons why users proficient in one software package have difficulty adapting to another program. Adapting to different workflows often creates confusion and frustration, as illustrated by these forum posts by irate users. Although both methods can result in similar forms and can output files compatible with most CNC and rapid prototyping systems, each privileges certain design solutions. The aesthetic implications of these processes is obviously relevant here, but beyond the scope of this paper, which I'm attempting to focus on process rather than product. So this is SolidWorks interface, which I'm just going to talk through if you just watch that. In solid modelling system, objects are defined as geometric masses that are typically created by extruding a 2-dimensional sketch along a 3rd axis. Solid modelling tends to be parametric, meaning that it is dimension driven with parent-child relationships. Dimensions can be numerically input as well as derived from other dimensions. Solid modelling tends to be more concerned with function rather than aesthetic design, and is typically used by engineers. This is rather short on here, sorry. In surface modelling, objects have a 0 thickness skin that is formed from a set of points by lofting and sweeping between them. And points operate as a control mesh for surfaces that define forms. The This lends itself to curved and fluid forms that can be positioned visually rather than mathematically. They are generally not parametric and have no child-parent hierarchy. The distinctions between these two examples are evident in our simplified software examples of 1, 2, 3 design, which are shown here. As with professional surface modeling software, 123D Sculpt provides a set of geometric primitives which the user can manipulate by selecting a variety of tools. The control points and other advanced features are not accessible on the iPad, but the form can easily be pinched, squeezed, and shaped to desired shape, as you can see in the lower video here. The plastic nature of surface modeling not only has obvious parallels in physical and media processes, such as clay modeling, but also allows similar workflows from the generic to the specific. So it's a sort of core function that I'm wanting to get at here, which is this direction of accruing a form. This is more evident in contrast. 123D design, so at the top here, does not allow for push-pull deformation, while dimensioning is not fully parametric on the iPad. The software follows the constructional logic of solid modeling. Forms are built by selecting and extruding surfaces. As with 123D Sculpt, the user can select from a menu of primitives which can be positioned but not deformed. The workflow here, however, is from the specific to the general. So these two things are working these two methods are working in opposition to each other. I've got two buttons. This is more evident in the professional solid modeling packages, where parts are built from 2D sketches and combined into assemblies that constitute final designs. Solid modeling has obvious parallels to additive construction methods, where components, metal and wood, are dimensions and stuck or welded together. While surface and solid modeling have clearly different methodological approaches, they have parallels in physical media practices. This knowledge does not necessarily transfer between the two equally. While a tacit understanding of modeling in clay may develop an ability to think in the round, I've seen nothing to suggest that this translates to surface modeling methods. In contrast, solid modeling's additive method appears to support and even enhance an understanding of physical fabrication processes. This is clearly seen here in a recent exercise by Year 1 students, creative technology students, who were asked to make simple mechanical designs. In this 1-week exercise, students were beginning to learn SolidWorks, where we're introduced to core mechanical principles, levers and cams and gears, etc., and asked to produce a CAD design for a simple automata. So you can see here various sort of clusters of projects, including sort of renders from the CAD software and the laser templates and the final cutout assembled parts. As is evident in these notebook sketches, the students frequently had poor, can you actually see those? Can you see those drawings? Yeah. As evident in these notebook sketches, the students frequently had poor hand drawing skills that limited their ability to understand mechanical principles. While the drawings can also be said to reflect a poor mechanical spatial understanding, their ability to develop working models in SolidWorks suggests that the solid modeling enhanced their understanding. I suggest that by providing a structured environment, solid modeling that demands dimension-driven accuracy progresses from the specific to the general and produces simulations. Students were confronted with making decisions that advanced their mechanical knowledge and enabled them to physically realize their design intentions with laser cutters. Although the use of laser cutters undoubtedly overcame a lack of physical fabrication skills, the structural method of solid modeling promoted an approach that enabled effective design thinking. The result of this could be seen in the responses to the following brief, where the complexity and ambition of mechanical designs were indicated by strong mechanical principles. So this is a subsequent project that was developed where the levels of interconnectedness and the development has been obviously enhanced and engaged from those initial experiments. This is clearly in contrast with a student working without CAD who turns up at the workshop with the exact sizes of parts drawn out on a piece of timber, not realising that saw will remove several millimetres of from the dimensions, that they are unprepared for the level of decision making required to realise their idea. In addition to the approaches I've discussed, I now want to touch briefly on the implications of generative modelling methods. And also something of a train. As well as solid and surface construction methods, many CAD packages allow for various forms of generative modelling. Generative CAD processes take sets of data and mathematical equations as parameters for defining form. This is especially useful for designs that feature complex geometric patterns or parameters that are subject to time-based modification. Here you see a sort of very typical example of the type of output from Rhino 3D using a plugin called Grasshopper, which has a graphic interface for programming the mathematical equations. So this mathematical construct here is just constructing that 3D form. There is nothing else that's defined there. In considering the work of recent creative technology students, similar affordances to those discussed in regard to solid modelling can be seen. Students were able to realise forms that were either inappropriate to hand sketch or existed as mathematical concepts rather than forms. However, unlike solid modelling, that appears to promote transferable knowledge. Generative modelling appears to create a disconnect from the material artifact. While in this example on the left, a student was only able to express their idea algorithmically, they were able to program mathematical complex structures using multiple segments and struts. So again here, this has been generated in Grasshopper, and it's the student was unable to really conceive it in a drawn manner, only in a mathematical manner. In the gravity-free void of CAD environment, the model appears to be a robust response to the brief. However, as a 3D print, the realities of gravity sadly reduce the work to a pile of dust and thin sticks. Obviously, generative modelling sits one step too far removed from the material realities of the world. So, when you reflect on this, obviously there's nothing actually sustaining the spaces between these different levels. It's like a very large spring, but without any tension in it, and the whole thing just sort of claps and was never actually been able to take out of the printer that it was made in. Although not quite as dramatic in their structural failure, other projects showed similar methodological breakdowns. That is, I propose, due to the abstract nature of generative modelling. Well, on the one hand, we can see that this failure to understand physical properties can also be seen as demonstrating a good understanding of digital materiality that is inherent in the CAD environment. The problem comes only when it is transferred into a physical artifact. Students were also asked to provide renders of CAD designs along with their finished 3D print. What is clear in viewing these renders, which are shown here as well as the 3D prints, is that students were more interested in the details of the models than the governing structures. So these images in the centre are the structures that were produced, whereas the other images are close-ups that they shot from within their rendering. The renders they provided of organic spirals and convoluted interiors are like images from electron microscopes and as inaccessible to the naked eye as they would be to the hand. We simply cannot see that much detail without magnification. The scalar distancing that generative modelling creates between abstract methods and outcome further de-emphasises the significance of the resulting forms. In film candidate Gerbrand van Mierle's experimental sound loops make no attempt to preconceive aesthetic outcome. Here, frequency value from 16-second sound loops are fed into a series of control points defining the torus. The resulting artifact exists as some frozen encapsulation of its audio source. It deliberately lacks aesthetic intent and defers to material and process-driven concepts in the same way that action practices, art practices of the 1960s. Its conceptual premise justifies any resulting form. Scalar ambiguities, I suggest, are also part of the inherent material quality of CAD processes, and together with a suspension of structural integrity, indicate the emergence of a materiality of CAD that must be reconciled as we seek to integrate these systems into material practices. In this brief analysis of projects by students from AUT, I've tried to identify primary methodological constructs of CAD and its relationship to established physical work practices. Many complex issues, such as the nature of junctions, chance, and malfunction, have been left out in an attempt to focus on these larger constructs. I've suggested that Cartesian space of 3D modelling environments both distances CAD design from material processes while connecting it to Cartesian logic of machinery. I've also proposed that surface modelling workflows with clear parallels to plastic media processes do not necessarily result in transferable knowledge, while solid modelling workflows foster an understanding of mechanical and structural function. In regards to generative modelling and abstract methods that bear comparison to conceptual practice, I've hinted at a material sensibility for CAD that brings it into the workshop. Finding space on the workbench for computer-aided design is not then simply a matter of dusting off a surface and hanging up a few hand tools. Rather, it is the underlying structural methods that drive these new technologies that need to be understood. In doing so, we may be surprised that they are just as dusty and smelly as other material processes. Thank you.
Do practitioners kind of, they're not the new students, right? Do practitioners end up getting the sensibility if they come from one direction, or is it just you go off in one direction and you become a CAD designer and you're kind of lost in this is the fixable and I deal with this very geometric thing?
Are you saying like that there's a divergence here point where sort of people sort of go, okay, well, I'm either going to develop things by hand or I'm going to develop by CAD?
More like if you pick up, if you didn't pick it up, can you pick it up later a little bit?
Sure.
Does it integrate?
Yeah, I mean, I picked it up. I mean, it didn't exist when.
Sure, it didn't pick it up the other way as well, right?
I mean, certainly you can, but I mean, I also when I first started making things in CAD, I would be very frustrated because I couldn't, even though I could make stuff, I would find that the software was designing stuff for me.
You limited by the tool?
Yeah, and that I would go back into the workshop, make that stuff in materials that I was conversant with, and then go back to CAD and simulate it. I mean, there's obviously lots of issues and problems around that, but yeah, it's a sort of frustration you can do.
Do you find yourself doing that a lot, going from form back to a digital then? Or is that a learning curve, and once you pick it up, you pick it up?
I think after a while you get to sort of conceive and thinking in that way. But on the other hand, if you're working for 3D printing something or CNCing it, you're always projecting into a physical material. So you're always working with, okay, well, this, especially if you're just sort of doing robotic type stuff, then motors have fixed diameters, you're fitting into those, you're sort of aware of those physical features that you're accommodating.
I really appreciated the comment about the possibilities of mathematical approaches to fabrication as opposed to, I guess, for lack of a better word, non. Can you elaborate? Like, is there one that sticks out, like where the use of desktop fabrication methods affords a creative mode of production or a creative form that wouldn't be afforded by hand?
Sorry, can you say it again? I lost
you after that. The emphasis on the mathematical.
Yep.
I mean, because you read a lot of the literature around desktop fabrication, right? It's usually around like speed and pace, and maybe your really great critique of the language around like hobbyism, like you can just dive in and print anything, is really misleading. But your point about the possibilities of mathematical design methods and what they might afford the non-mathematical approaches, what are manual approaches might be a better way of putting that. Do you have like a case study or an example that really sticks out as like you could only do it through this mathematical approach?
No doubt, like for example with Grasshopper, no doubt you could very time intensive reproduce, for example, down a lofted curved wall. You can mathematically distribute with variations a grid down that wall, as a sort of tessellated grid down the wall. And you could do that by hand. I mean, if you were doing it by hand, you'd have a totally different methodology, which would not be to start with a plane, but would be to start with a unit and repeat that.
Right.
So rather than I think saying you can't do it, it's about the way that you go about doing it and the implications that then has on how the form turns out. I mean, we're talking in a creative context. We're not usually talking about a predetermined outcome. We're talking about an immersion process.
Right.
So, when you've got software feeding into that, the way that pans out is quite different. Those methods. I'm quite interested in that idea of that aesthetic, maths defining aesthetics.
Yeah.
Yeah, you talked a little bit about the frustration of students who are building things in virtual spaces and then they print them out and they have no sense of sort of the weight or the structure of them and they just crumble. Do you get any advantage from people who maybe are not particularly dexterous or careful that find that this is sort of liberating to them, or this makes for a bigger tent of people that could presumably be involved in fabrication because they have the benefit of the undo button?
Yeah, but it also has to be done. And I think what students find is that, and what I was trying to indicate was that the demands of the software, it's like, no, I want to know exactly how fucking big I am, not just sort of vaguely how big I am. I want to know exactly. And especially if you're doing mathematically, close enough is not near enough. And so you just can't do so. It doesn't, it's not like it's sort of, you wave your hands in the air and this thing comes up and then it doesn't print or whatever. If you can't do it in the solid state, there's no, in the modeling state, there's no way then it's going to go anywhere near a printer. So there's a rigor to solid modeling in particular that preempts some of those failures, although the zero gravity phenomena doesn't.
Yeah.
There's also an issue of cost. Students invariably try to reduce wall thickness down to as thin as they can to reduce cost, because cost is based on material use. So the thinner you make something, the less it costs. So you end up with sort of floppy forms.
Thank you.